In this segment, I want to explain the idea that matrices are useful at describing linear transformations. Let's pick a linear transformation that we call F that goes from Rm to Rn and that maps a vector x onto its image f of x, which is itself a vector, in a linear way. And that means that if we apply f to a linear combination ax plus by, then that will come out as the linear combination of f's, meaning a f of x plus b f of y. This is what a linear map is. Now, any such linear map must be written as the matrix product A times X for some matrix A. In fact, this is the reason the matrix product is written in its form. It's because it encodes linear transformations on vectors. So that ends up being the most general way of writing such a linear transformation. It's with the matrix vector product. So let's see a few examples of that. Let's start with a case where the input space would be two-dimensional and output space would be three-dimensional. In this case, our matrices are going to be 3 by 2. Let's take an example here. Matrix A, that would be the following, for instance. Let's pick the elements 1, 2, 3, 4, and 5, 6. And so the dimensions need to match for AX to make sense. Here X, therefore, in the input space Rm needs to be two-dimensional. Let's pick it to be the vector 1 minus 1, for instance. And if we go ahead and perform the matrix vector product, we'll see that Ax needs to be the vector where you have 1 times 1 plus 2 times minus 1 and so forth. We do all these operations and we end up with a vector minus 1, minus 1, minus 1. So that means that the matrix A encodes a linear transformation with the matrix vector product. So what we want to do here is see a few examples where we can understand what the linear transformation is that correspond to any given matrix. So let's see an example now which is in 2 dimensions and corresponds to the following matrix. So let's try to see what happens with the matrix 2, 1 on the diagonal and then zeros off the diagonal. What kind of linear transformation corresponds to that matrix? And in order to know what that may be, one useful thing to do is to apply this matrix to a few different vectors in the plane and see what happens to them. And so here we can, for instance, choose the vector 1, 0, the canonical basis vectors, here 1, 0, and then 0, 1 for the second basis vector there, and then see what happens to those vectors. That will give a good indication of what the linear transformation does. So if we go ahead and apply A to the vector 1, 0, that operation selects the first column of A and we end up with the vector 2, 0. And on the other hand, if we apply A to the vector 0, 1, then that will be unchanged. We pick the second column of A, that is still going to be 0, 1. And so that means that if we want to visualize what the result looks like, we are going to distort here our unit circle into an ellipse that looks something like this. And so here, for instance, the vector 1, 0 was mapped into the vector 2, 0. Here it is. And the vector 0, 1 is unchanged. And so here it is. All the other vectors undergo an operation that is a combination of those two, and so you end up having a mapping of shapes now generated by this matrix A. In fact, you can understand that these vectors, canonical basis vectors, play special roles. If you look at this expression here, you'll see that you in fact are looking at the statement that 1, 0 is an eigenvector with eigenvalue 2. And here you're looking at the statement that 0, 1 is an eigenvector with eigenvalue 1. So those are the vectors whose direction is unchanged when you act with A on them. And those are the special directions here for the linear transformation. There's a stretch along the x-axis, which is an eigenvector, and there is no stretch along the y-axis. If you pick any other vector that's not an eigenvector, you have a combination of these operations in such a way that the direction of the vector is changed upon the application. And finally, if you want to know the mapping of areas, the area scaling factor for this transformation, what you do is you compute the determinant of A, take the absolute value. In this case, is going to be 2. The areas are doubled under this transformation. Okay. So that's what happened in the case when we had this stretch here, so dilation in one direction. Let's see another example, still in 2 dimensions, where we now are going to do it the other way around, and we're going to start by specifying a linear application, a linear map, and we'll try to find the matrix that corresponds to that. So let's try to find a matrix that corresponds to a rotation of 90 degrees in the plane. We're going to ask for this rotation to be counterclockwise. And the way we can get at the matrix for this transformation is by, again, finding the result of that linear map on specially chosen vectors. And again, we'll pick the 2 canonical basis vectors here, 1, 0 and 0, 1, and see what happens to them upon the transformation. So here, if we do a rotation of an angle theta counterclockwise, we'll end up having a vector whose coordinates now are going to be cosine theta, sine theta. That's what happens to the first vector. And for the second vector here, if we apply rotation of an angle theta to it, we'll end up ending with a vector whose components are now going to be minus sine theta and cosine theta. And this is enough to specify the matrix, because if we apply the matrix A, again, I reuse the letter A here for this example, to the vector 1, 0, that is picking the first column of it. While if I apply A to the vector 0, 1, that selects the second column of it. That's why those vectors are particularly interesting in this example. And so as a result of that, because we know what those images are, we can form the matrix as being cosine theta, sine theta, minus sine theta, and cosine theta. That is our rotation matrix here. If you wanted to do a clockwise rotation, you would swap the sine of theta, which would correspond to displacing the minus sign from this location here to that location over there in front of the other sine theta, if you wanted to have the other rotation clockwise. And so this is a very standard result about rotation matrices. This is what they look like in 2 dimensions. It is difficult to understand what happens to the linear transformation from the eigenvectors, because here in this case we do not have real eigenvalues and we do not have real eigenvectors, and that's how it should be. Rotations do not preserve the direction of vectors. There is no vector in the plane whose direction is preserved under the action of A, and indeed the eigenvectors are complex. So here this is not an analysis that will be immediately useful to tell us about the linear transformation associated to this matrix A. Okay, so there are many more examples that we could cover. Let's take another one which is also quite representative of what a matrix can do to a vector. Let's pick again in 2 dimensions. Now an example with the matrix is a so-called Jordan block, where we have the matrix 1, 1, 0, 1. And let's try to visualize what happens in the plane when we act with this matrix on vectors. And let's do it by considering this time maybe the unit square. So let's pick again our 2 favorite vectors here, 1, 0 and 0, 1. And let's also pick the vector 1, 1. And let's see what happens when we apply the matrix A to those. If you apply the matrix A to 1, 0, you are going to pick up the first column of A, as we said, so that is unchanged. That stays there. And now if we apply A to the vector 0, 1, that will pick up the second column of A, that becomes the vector 1, 1. So that vector here gets mapped to this vector there. It gets mapped to 1, 1. And if we use the input vector 1, 1 and we apply the matrix A to it, then what we'll see is that we end up with the vector with components 2, 1. And so that means that we'll have the following shape being created out of the operation encoded by the matrix A. Here's our vector 2, 1. And so that operation is called a shear. There is one way to understand the action of A on its eigenvector. There is a single eigenvector for this matrix. It's the vector 1, 0. We've already seen that that is unchanged by the matrix. That corresponds to the eigenvalue 1. This eigenvalue is double but there is a single eigenvector that corresponds to it. This is a situation where we say the matrix is deficient. So there will be no other vector here in the plane which will be unchanged or will preserve its direction if we act with the matrix A on it. That's what the shear does. All right, let's see another example. Now we're in 3 dimensions, m equals n equals 3. And the transformation, now let's start from f again. And let's say that we want to understand the map that takes a vector with components x, y, z and returns the vector with components x, y, 0. This is going to be a projection where the third component is put to 0. In other words, it's a projection onto the xy plane. Let's see what matrix corresponds to that. Again, it's going to be a game of applying this linear transformation to a few properly selected vectors in order to form the whole matrix out of that. So let's apply that to the vector 1, 0, 0. We see that that is unchanged because it already belongs to the xy plane. So we are, in fact, again, quite luckily in presence of an eigenvector of the resulting matrix. We see that the vector is unchanged and the eigenvalue is 1 here. And that will give us the first column of the matrix A. And then if we apply f to the vector 0, 1, 0, then that is also unchanged because it belongs to the xy plane. So we're in presence again of an eigenvalue equal to 1. So that's going to be a double eigenvalue, but this time you do have 2 eigenvectors for it. So that is not a deficient case. It is a regular case where you have an eigenspace of dimension 2 here at the xy plane. And finally, if we apply the map f to the vector 0, 0, 1, that is along the z-axis, and when we project onto the xy plane, that lands at the origin. So here in this case, we have a third eigenvalue equal to 0, and that will give us the third column of the matrix. And the eigenvector that corresponds to this third eigenvalue is 0, 0, 1. So we go ahead and form the matrix from these columns that we've gathered, and we have 0. You have 1, 0, 0 for the first column, 0, 1, 0, and then 0, 0, 0. That is the matrix for the projection onto the xy plane. And the eigenvectors, again, play an important role here. In the description of the geometry of what the transformation does, we have a projection along the z-axis along 0, 0, 1, this third eigenvector here, and the projection is onto the xy plane, which is going to be the space spanned by the first 2 eigenvectors. So we can denote that as the span of 1, 0, 0 and 0, 1, 0. So that's the xy plane. So those eigenvectors, again, are completely specify the operation that we have. They give the geometry of what the projection is. If you remember, in the case of our stretch some time ago here, we had the area scaling factor equal to 2 by computing the absolute value of the determinant. If you do that with this matrix here and you look at the absolute value of the determinant of A, you get 0. This is a singular matrix, and indeed this is now the volume scaling factor in 3 dimensions. And if you have any set whose volume is non-zero, and then you apply projection to it, this projection, you will squish it and you will not preserve the volume. The volume becomes 0. So indeed, that corresponds to the fact that the determinant is 0. So in all these cases, we could look at many more examples. In all these cases, it is sometimes, but not always, useful to consider the expansion of A in terms of its eigenvalues and eigenvectors. And so the general way of writing that down is to say that the matrix A acting on the matrix of its eigenvectors, we'll say it's a matrix S here, whose columns are the eigenvectors of A. That results in a scaling of the columns of S. And so the way that's written in matrix terms is by writing SD, where D is a diagonal matrix with the eigenvalues on the diagonal here and 0 elsewhere. And so indeed that corresponds to the decomposition of the matrix A, and that helps us understand it as a linear transformation, because if we apply A to a vector X, we now have the expression that when S is invertible, when there are enough eigenvectors, then we can write SD S inverse applied to the vector X. And now this is provides oftentimes a good way of understanding the linear transformation, because what you're looking at here, the operation S inverse X, is really the way to compute the coefficients of X in the basis of eigenvectors. so the coefficients of x in S. This is what this quantity is, S inverse X. So you are doing a change of basis so that the matrix is diagonalized, is decoupled. Indeed, it becomes the action of the diagonal matrix onto that vector of coefficients. So we are talking about scalings now encoded by this matrix D. The lambdas, the eigenvalues, provide the scalings to be applied to the coefficients of X in the basis of eigenvectors. So that's what happens after you've applied D to S inverse X. And finally, the last operation is to apply the matrix S to that, and all that does is it undoes the basis of the change of basis that we started from, so it recombines it into a proper vector in the output space. So this is the combination or the synthesis step of the factorization of A. And so again, we had a useful point of view with the eigenvalues, eigenvectors, in the case when we had here the stretch. Not so much when we had the rotation because we did not have real eigenvectors. We had a partial picture when we had the shear operation because we had a deficient matrix. There was only one eigenvector, and we had a full picture in the case of the projection here. So it's always a good thing to compute if you want to understand the matrix A as a linear transformation. All right.